So we come to the last chapter that we need to study, which is Laws of Thermodynamics, chapter 12. This chapter is quite a large chapter. You will learn the three main laws of thermodynamics. You have already learned the zeroth law, right? Zeroth law was about thermal equilibrium, and we did it in the chapter about temperature. So we're going to start with learning the concept of work, and let's just remind ourselves of some definitions, okay? So we know what internal energy is, the symbol U, you have been using it. It represents the sum of the total energy in the system. So the system needs to be defined, and you're going to take all the kinetic and potential energies in the system, sum them up, that's your U. This internal energy depends just on the state of the system. So typically we're going to be talking about a gas. We're going to have a gas doing the work, and the state of the gas depends on P, V, and T. We saw that earlier, right? So the potential, the total internal energy U is just a function of state. Yeah? It does not depend on the path by which we change states. Yeah? It depends on the initial and final states. Does not depend on how you go between one and the other. So we say it's path independent. Q represents heat. This is the energy transferred in or out. So positive if it's transferred into the system, negative if out. And it does depend on the path of the system. W is the work done either by the system or on the system. Okay. So it'll be positive when the work is done on the system. So the system gains energy, and it'll be negative when it's done by the system loses energy. It is path dependent. Okay. So let's say this green box here contains my system, and I feed in some energy at a certain rate. So Q is my energy that I feed in. And let's say work is done on the system by maybe compressing a gas, okay? So I'm working on the gas, that work is fed into the system, then the change in internal energy of the system is nothing but the sum of these two. So we're going to say delta U equals Q plus W. This is my first law. And we need to be careful of signs here. Right? I talked about the sign of Q earlier when it gains energy. So energy is coming in, Q is positive. Energy is going out, Q is going to be negative. Similarly, work done on the system is going to be positive. Work done by the system is going to be negative. And that will determine the sign of delta U, right? And delta U also varies directly with temperature. So if my temperature is increasing, delta U will increase. Temperature is decreasing, delta U will decrease. Okay, so the first law of thermodynamics tells us that the internal energy, U, of the system can be increased by adding energy to the system, which is Q, doing work on the system, which is W. There are many processes through which this can be accomplished as long as energy is conserved. Okay, so we're assuming that in this whole set of energy is conserved because we have an isolated system. Delta U is always expanded as final minus initial, just writing the same thing equals Q plus W. And we're talking about the signs here. I've been through this with you, right? Let's do a simple problem on this. Let's say we just do part A and then you can do part B. Suppose there is a heat transfer of 40 joules to a system. So I'm going to make my system, let it be this box, and I'm going to transfer in some Q, which is 40 joules. Yeah? While the system does 10 joules of work. So the system is doing work. Let me change the color for that to maybe green. So this is energy that's being lost by the system. Work is being done worth 10 joules. Yeah? This energy leaving the system. Later, there is a heat transfer of 25 joules out of the system. So some heat also goes out of the system, 25. So in green, we have everything going out. In blue, we have things coming in, or energy gained by the system. while 4 joules of work is done on the system. So 4 more joules of work is done on the system. These arrows are not to scale, obviously. What is the net change in internal energy of the system? Now I just need to sum this up. So here I have 44 joules going in, and I have 35 joules coming out. So the out is going to be negative. I just need to do 44 minus 35, and that's going to give me my result, which is going to be 9 joules. Okay, so now I want you to think through the next problem and compare your answers with mine. That's 9 joules for the first part, and the second part also gives you 9 joules. So work in a thermodynamic process, if we're dealing typically with a gas, we're going to assume that while we're compressing or letting the gas expand, it always happens at every step in thermodynamic equilibrium. What does that mean? That means that the system remains isolated, no energy transfer with the outside, okay? And so we are doing this process of compression or expansion in a very slow fashion so that the gas is constantly in equilibrium. Some parts of the gas are not hotter than the others. And if it's in equilibrium, thermodynamic equilibrium, then the gas law applies. We're going to use the ideal gas law, PV equals nRT. Okay, we're going to say that this always applies to the gas at every step, not just at the first and the last step, but every in-between step. So here's a cylinder. We've cut it in half so that you can see the inside. This orange thing is the gas. This is a piston that can move up or down. So I have a certain volume. If I compress it, then I'm lowering my piston by an amount, say delta Y. And then the pressure and volume are going to change, right? Because the pressure is going to increase, the volume is going to decrease. And I have done work on the system by pushing the piston down, yeah? So when you compress the gas, you do work on the system. And how much work was done? That is actually given by P delta V, and the negative of P delta V, where the pressure, let's say, remains constant, and delta V is the change in volume. If you want to see how this is work, you can convince yourself that this is equivalent to work in units because, say, work equals negative P delta V, and pressure is nothing but force per unit area. So force per cross-sectional area A, that's shown here, okay? And delta V is that same cross-sectional area A times delta Y, the change in height, yeah? So I can cancel out these two A's. That leaves me with negative F delta Y, yeah, is my work done. So this is force times distance. This is what you learned about work, force and distance in the same direction as the work, yeah? Delta Y is Y final minus Y initial, so Y final is lower. We're going to get a negative value, the negative from delta Y, and this negative are going to get multiplied into a positive. So positive work is done on the gas, or the gas gains energy, yeah? When we are compressing the gas. And exactly the reverse happens when you allow the piston to be free and the gas does work to push the piston up. Then the gas does work and W becomes negative. Okay. So gas is compressed, delta V is negative, the work done on the gas is positive. When the gas is allowed to expand, delta V is positive, work done on the gas is negative. It's important to be able to work out these symbols of positive and negative. When the volume remains constant, then no work is done on the gas because work is defined as P times delta V. If delta V is 0, then work is 0. So let's do a simple problem on this. Gas in a cylinder moves the piston of area 0.2 meters squared as energy is slowly added to the system. Okay. So the gas is doing work to move the piston and energy is also being added to the system. if work of so many joules, if so many joules of work is done on the environment and the pressure in the gas remains a constant 1.01 times 10 to the power 5 pascals, find the displacement of the piston. Yeah? So you're going to do work equals P delta V, yeah, P delta V, and you're going to solve for the displacement delta X by changing delta V to area times delta X, which we did before. And then it's just a question of putting in the numbers, manipulating to solve for delta X, and you should get exactly what I got. So W equals negative P delta V. Okay, this is our work equation, and it assumes that the pressure remains constant. When the pressure remains constant, this is called an isobaric process. So pressure is sometimes measured in bars, in units of bars. Iso means the same. That means same pressure, isobaric. Yeah? So this work equation applies to the isobaric process. Since P delta V is the work done, if we plot a PV diagram, okay, how the pressure varies with volume, then we start with some initial state, and let's say we compress the gas, then we go to a lower volume state. This is my curve or the path along which the compression happens. So P delta V is this entire area, correct? The shaded area. You can convince yourselves of that. Yeah? That means the shaded area gives me the work done on the gas when it's compressed and by the gas when it's opened out. So the area under the curve. If it happens to be a closed loop, it's going to be the area inside the curve that will give me the work done. We'll see some examples of that later on. So we can find these are a set of PV diagrams, pressure, volume, 4 of them. In each case, our initial and final points are the same. So we have two states we are going between. Sorry, beg your pardon. Initial and final may not be the same. Because we are sometimes going, the arrow is going to the right. That means this is my initial state, this is final state. Here I see that the arrow is going to the left. That means this is my initial state, this is my final state. But we have the same 2 points, okay? You can convince yourself that these are the same points everywhere, yeah? So we're going between two states, right? And we're going in different ways. So the path is different. This is one path, this is another path in the opposite direction. This is another path, the same way as the first one, but a different path from the first one, and then this one. What about the work done? So we saw the work done was the shaded area under the curve. And you can see that these are all different. Yeah? So given the distances here, you can actually calculate the work done as the area under the curve. And that's the next thing we're going to do. So let's do one problem here. Compute the work done in the PV diagram shown. And I know, sorry about it being slightly fuzzy, not perfectly in focus. But my work done is going to be negative P delta V, right? Or area under the curve. So I'm going to split my area right here. Let's say, oh, sorry, let's not split here. Let us split along here. Then I have this triangle and I have this rectangle. So I just need the area of this rectangle, and that's going to be 1 unit cross 2 units, yeah? So we're going to get 2 times 10 to the power 5. Don't forget that, yeah, because this is 1 times 10 to the power 5. Let me just correct that. Okay. So 2 times 10 to the power 5 joules, since we're in the MKS unit. And what about this area? This is half base into height. So we're going to do it here. Half base is 1, and the height is going 2 times 10 to the power 5. So this is just going to give me 1 times 10 to the power 5. Yeah? Joules. So I can add this and this. That gives me a total of 3 times 10 to the power 5 joules should be my work done. Yeah? Okay. Let's see that. 3 times 10 to the power 5. So that's how you're going to solve these kind of problems, by calculating the area under the curve. You can go back for those 4 diagrams that we had before and try to do some of those by yourself.